Hello and welcome to this lecture number 54 of our course on blockchain and its applications. Also, this is the third and final lecture on the particular topic of blockchain security. So, the topics that we plan to cover, the basic concepts that will be included in this particular lecture are essentially two types of attacks. One is what we call as front running attack and the other is eclipse attack. We will first discuss about the eclipse attack and then we will go into the details of front running attack. And of course, other than eclipse attack and front running attack as the keyword, we also have these two other keywords like peer to peer network, which will show that it is something that is of importance in the context of eclipse attacks. And for front running attacks, we will talk about different types of front running attacks, which we denote as displacement, insertion and suppression. Just to give you the context once again, that in this particular topic of blockchain security, we are discussing different such general types of attacks, some of which could be there in general for, as we mentioned, that it could be for like 1.0 and 2.0, these generations of blockchain. And of course, we are not talking about specific types of attacks that pertain to this blockchain 2.0 like the smart contract. So, that is the context. Also, in the first lecture on security, we talked about the different types of attacks. We mentioned the different types of risks like 51% vulnerability and like privacy leakage and so on. So, in that context, we are actually talking about two such new types of attacks which we have not yet discussed. And if you remember, in the last lecture we talked about selfish mining attack, which was again another type of attack. So, here what we will do is that we will first talk about eclipse attack and see how it is carried out and what it is all about. Before we start the discussion on it, I would like to remind you that it is best to take a look at this particular paper, which is on eclipse attack, and it was published in one of the top security symposiums, which is called Usenix Security Symposium. And it is a very well written paper, and it is very important that you go through this to get more details about what we are discussing in the class. One point that we must make when we talk about eclipse attack, if you see that most of the other attacks that we have talked about, and also the next one called front running attack that we will discuss today, these are at the higher application level protocol of blockchain, meaning that they are not really going to attack the basic way the peer to peer network is set up for a blockchain. If you remember that we said blockchain is a distributed ledger, it is completely running on a peer to peer network. So, this particular attack, this eclipse attack, this is going to make use of some, you call it vulnerabilities or some characteristics of this setting up and maintenance of the peer to peer network that is embedded in these blockchain protocols. So, it is going to actually attack those types of vulnerabilities, and that is why it is completely different from the all other types of attacks that we are talking about here. What is done here in this eclipse attack? So, there is an identified victim. The attacker has identified a particular victim which is shown here, that is a to be victim node. So, in normal situation, how do we generate this particular network of these peers, that when a new node joins, if you remember, we discussed it in our discussions in the context of elements of blockchain, where we said that when a new node joins, of course, it installs the software like the Bitcoin software, then it tries to reach out to different other nodes and then set of those nodes form its peers. So, we have in this example that this node in the middle that has got a number of such peers, and initially let us assume everything is really nice, and then we do have this particular situation where these are all normal or honest nodes, and this is a node which does not know it is going to be a victim. And of course, that through its peers like say this one, this one, this one and this one, this particular node can communicate with this one and again through another hop maybe through this one and so on. So, that is how it is actually connected with the entire blockchain network. Now, what happens is that now in Eclipse attack there is an attacker node. What it will try to do is that it will try to ensure that it and its controlled other nodes, they only be the peers of this victim node. That is the whole goal of this attack. So, what attacker will do is that it will now try to join this victim node as its peers. So, what we see here is that initially we have these two attacker nodes that also have become peers of this particular victim node, and then so it starts with that, and slowly what it will do is that it will ensure that it gains full control over that information about who are its peers or its neighbors. So, the attacker starts with maybe one or two nodes first being peers of this would be victim node, which now is going to be the victim, and then after that it will ensure that this victim node will not be able to communicate with the outside world except through these peer nodes which are all controlled by the attackers. So, if as we can see now in this example that if this victim node wants to communicate with this, it has to go maybe through this attacker node, and if it has to go through this attacker node and also if it has to receive anything from its this particular node, then also it is passing through this attacker node. And in that case what will happen is that the attacker now decide what part of the information, which part or which state of the chain to be made available to the victim node and which part of the chain it will not make available to the victim node. It can control whether the transactions from the victim node will indeed reach the rest of the network to be included in the in any other block. So, if some of these attacker nodes are also doing the mining, what they will do is that they will selectively may drop some of the transactions of this victim node, or they may decide to include something depending on what is going to benefit them. So, that is what this attacker is actually trying to do when it is carrying out this type of attack. And after some time when it has actually completely covered this victim node, that it will be able to manage the entire flow as is shown here in an abstract way, that now the victim has been isolated from the rest of the network and the attacker node is sitting in between, and that is why it is called an eclipse attack, where like eclipse now this attacker is shadowing the entire victim node and then it is not letting it actually communicate with the rest of the network without it being able to mediate whatever it wants to go, either from the victim node to the rest of the network or from the rest of the network to the victim node. So, once this attacker is able to control the victim node, so what it does is that it is actually controlling the path from the victim node and the rest of the network. It is not actually completely devastating the full infrastructure between the victim and the rest of the Bitcoin network. So, it is letting things pass, but it can selectively decide which part to maybe suppress and which is not to be suppressed. So, that is why it is not a full key network infrastructure that is actually completely blocked or made unavailable to the victim node. It is just that it is coming in between, in the path between the victim node and the rest of the network. So, the question would be that why would the attacker do this? So, this is the interesting part, that if you see that if the attacker could actually get 51% of computing power, it could control the entire network. But in this example, as you can see that say the attacker does not have 50%, it has got only 40% of hashing power. So, what as we write here is that the benefit is that 51% attack can be carried out with say as an example with 40% mining power. So, do not take it literally that it is only with 40%. In this example it is like that, but it could be depending on the computing power of the Eclipse node and the rest of the network. So, what we show here in this example, say this particular victim node, suppose it had got 30%, and then the rest of the network had got 40%, I am sorry, that had got 30% hashing power, and this attacker node has 40% power. So, if you see overall this, the rest of the network and the victim node together had 60%, which was more than 40%, but by successfully separating out this particular victim node, what is happening is that now it is one to one, head to head between the attacker's hashing power of 40% of the overall and the rest of the network's hashing power of 30%. So, basically the attacker can now control what it otherwise would have required 51% of computing power to control. So, the attacker is partitioning the miners so that they can't build on each other's blocks. So, it is not possible for these victim nodes to add after the block that was mined by the rest of the network, or the rest of the network cannot add block after the one that was mined by this victim node. So, instead this attacker can now have more control as to which one is going to be added, because it has partitioned the computing power of the entire network. So, the attacker can now outcompete each of the partition miners individually. So, together if they could join or keep continuing mining. So, remember that they are not necessarily going to join hands and pull in their resources, they would independently try, and then sometimes this will succeed, sometimes that will succeed, but by doing this partitioning, attacker is ensuring that it will always be more likely to succeed. Of course, there is always an element of randomness in it, but the chances are of course now much higher for the attacker to actually do the mining. So, how it is done? The attacker populates the victim's nodes peer tables. Of course, for setting up the peer to peer network, it will need some peer tables where the IP addresses are there. So, the attacker will populate those tables with its own IP addresses, and when the victim node starts, it will lose its current ongoing connections which are with the honest nodes, and then as we had shown pictorially here, that initially it was like this with the honest nodes or normal nodes, then attacker is slowly taking charge, and in these diagrams whatever we have shown, that is like what we are talking about here now, is it is now going to change or update the list of peer nodes in that peer table by its own addresses. So, finally, the victim will establish all the new outgoing connections to the attacker's IP addresses. So, what it does is that first populates the IP address. So, each node, when it is trying to communicate with its peers, picks its peers from IP addresses stored in two tables. One is what is called the so called new table, the IPs the node has heard about, and a triad table, which is the IPs the node peered with some point. So, the tables also store a timestamp for each IP, and each table stores these IPs in the form of buckets. So, to find an IP to make an outgoing connection, to choose new or triad table to select from, select an IP with newest timestamp, and then attempt an outgoing connection to that IP. So, what happens is that attacker typically populates this triad table with its own IPs and the new tables with a bunch of some junk IPs. So, what will happen is that if the victim node first picks up from the new table, it will get a junk IP and where it cannot communicate with. So, then it will again try, and now it will pick up from the triad table, and now actually the attacker's IPs will be there in the triad table. So, eventually the victim will be picking up the attacker's IPs to communicate with. So, what it does is that it ensures a selection bias that more of attacker's IPs will get picked up, and if there is restarting of the node, and the restarting can happen many times due to security or software updates, or that there are some denial of service attacks. There is of course could be a network failure and or a power failure or ISP outage. We all know that from time to time we often restart our machines because we find something is not working, or we update something and then get a message that, oh, now you need to restart your machine. So, of course, there is always a need for restarting a machine, and when it is restarted, then all these tables will now get actually filled in with the IP addresses of the attacker. So, this what happens is that this, as I said, that these IP addresses will be filling in those tables. So, that is through this, as we said, that the IPs are stored in the form of buckets in those tables. So, a table will have certain number of buckets and each bucket will have a certain number of IP addresses. So, when the bucket is full, then some of these IPs are to be evicted. So, a bucket is full and an IP is also to be inserted, then it randomly selects a number of IPs, say 4 IPs, and then they delete the oldest IPs and insert new IPs. So, what we will do is that the attacker will ensure that the IPs that it has, so it will be having newer timestamps. So, these new IPs will get added to the bucket of the peer tables of this particular victim node. So, what can be done is that attacker IP replaces another attacker IP and so on, and attacker keeps refreshing the timestamp, so that all these will get added or get updated in the particular peer table of this victim node. So, if we want to ensure protection against this attack, so there are of course the authors of these research papers, while they show the how the attack can be carried out, they also try to explain that why this attack is being carried out, why the what vulnerabilities are being exploited by the attacker, and hence they also explain how one can actually try to guard against it. So, there are certain suggestions which are given as mentioned here, that eventually, so that the IPs are replaced by honest IPs. So, there are ways in which they can slightly change the protocol in which these buckets of IPs are actually updated. So, what people do is that the research community, they try to identify these vulnerabilities, different types of attacks, then they make it known to the developers like Bitcoin developers, and also suggest how these vulnerabilities can be fixed, so that they cannot easily be exploited by the attackers. And as they do this, then the developers, what they do is, like say Bitcoin developers, they will ensure that they possibly modify the protocol a little bit, or they try to fix a bug in their program which is causing that vulnerability to be there, which is being exploited, and then they make a next release of their software. So, this is similar to any other software where there are people who try to detect the vulnerabilities and then they report, and then they also provide fixes for that, and the developers actually come up with a new patch or new release altogether, and which all of us typically download, and then we are able to fix those bugs. So, that is what is also done, and the researchers they indeed did the same for this type of Eclipse attack for these blockchain networks. Next, we talk about the final attack, which is what is called front running attack. In front running attack, what happens is like this. So, in front running attack, I will explain what the steps are, but once again I would like to remind you that for this particular front running attack, please refer to this particular paper as is shown here, which is written on the screen, and this again explains this concept of front running attack in real detail, and it is very easy to read and also to understand. So, what we will do is that we will explain what is front running attack. Front running basically is a concept that if some party knows that something is going to be done in future, and based on that special knowledge which normally the others will not have, this one, let us call that as attacker, takes certain steps so that it gets benefited out of it. For example, that here the attacker sees that Alice is going to buy say some 1000 units of say ethers in the Ethereum network, and the attacker feels that if so many ethers are purchased by say one party, then the cost of this ether might go up. So, if it goes up, then if attacker later on tries to buy 1000, it will have to buy this at a higher price. Because attacker knows this particular information, so as we see here that attacker somehow gets to know about this information that this Alice is going to buy this particular Alice is going to buy this particular number of ethers. So, this attacker immediately what it does is that it now creates a new transaction that actually purchases those 1000 ethers. And if you see that maybe Alice was willing to pay a gas price of 5 joy, but the attacker says, oh, I will pay 50 joy, and then because it is willing to pay more for the transaction as the transaction cost, the miners will be willing to include the attacker's transaction before Alice's transaction. As a result, what will happen is that, let us assume that 1 ether was, just to take an example, was say 100 rupees, then if Alice purchased, maybe the price would go up to 110 rupees. So, before it goes up to 110 rupees, attacker is going to push in its transaction to buy it at 100 rupees. So, instead of paying this 110 into 1000 rupees, it got it at 100 into 1000 rupees, and that is what is called front running, because it is running in front of that other transaction. And how it could do it? It could actually do it by pushing the fact that it is now going to get its transaction before the other transaction. This particular paper, as we showed, that classifies these front running attacks into 3 types. One is what is called displacement, the other is insertion, and finally the third one is suppression. So, in the displacement type of front running attack, after the attacker's run, so attacker has carried out some transaction which we denote as attacker's run, Alice's function call is not important to the attacker. A typical example is like this, that say there is a website which is up for sale and Alice has said that I want to buy that website, but the attacker now gets to know that Alice is going to buy that. Alice, this attacker is aware of the transaction. What the attacker does is that attacker now instead purchases that particular website address. And of course, how can the attacker do it? Because the attacker knows, and because the attacker knows means it has already been done by say Alice. So, Alice has done means the transaction is there, but it is not yet confirmed in one of the blocks. So, it is there in the pool of transactions which are yet to be finalized, but the attacker knows it, and then attacker carries out the same transaction for its in its own name, say for buying that website address. But this, of course, by definition it comes after it is known that Alice had started that transaction. So, the attacker will front run it and try to ensure that its transaction of buying that website address goes before Alice's transaction, and it is to be ensured that it goes in it gets mined in a block before the Alice's transaction. And then what will happen is that once the attacker's transaction is executed, attacker gets that website address. When Alice's transaction will reach, so that address is no longer up for sale, so Alice's transaction will fail. So, whether Alice's function call is made or not, it is not important to the attacker. In insertion, after attacker's run, the state of the contract is changed. So, Alice's function call is needed to run on this modified state. It is same as this example we said, that say Alice was willing to buy 1000 ethers, and then so she was expecting to buy it at 1000 into 100 rupees, say at 100,000 Indian rupees it was planning to buy, she was planning to buy, but then attacker now purchased those 1000 at 100 rupees by paying 100,000, but then the price has shot up to 110. Now, Alice will be forced to buy at 110, and for that she has to pay more. So, what it says is that the Alice's function call will be required to run on this modified state. The state was 1 ether equal to 100 rupees, the modified state is 1 ether equal to 110 rupees. So, Alice's function call will be now required to run on this modified state. And in suppression, the attacker's run, after the attacker's run, so what it does is that the attacker tries to delay Alice's function call, and after certain amount of delay, it does not really matter whether Alice's function call really gets executed or not. So, this suppression type of attack, it is not very common, but we will talk about one such suppression type of attack, and you will be able to follow why that is also an interesting type of attack. So, these front running attacks also can be, just as we divided into these 3 types, displacement, insertion and suppression, they also can be divided into 2 types, asymmetric and bulk. So, all of these 3 types could be again further divided. So, like if there are these displacement, insertion, suppression, you can also have these differences or these 2 types of categorization into asymmetric and bulk. So, for example, asymmetric is Alice is trying to cancel an offer and an attacker is trying to fulfill it first. Say Alice initially made a transaction that I am willing to buy say 100 ethers, and later on she decided she will cancel it. So, attacker has enough ethers to sell. So, attacker can sell 100 ethers, but once the attacker sees that Alice is going to cancel that order, then the attacker will not be able to sell his 100 ethers. What it does is that it will try to front run Alice's that cancel transaction and ensure that his offering of these 100 transactions, which is what we have written here as fulfilling that order. So, the attacker will ensure that his 100 ethers are indeed actually purchased by Alice, because Alice's first transaction was willing to purchase and the second one was about to cancel that order. So, what the attacker is doing is that he is front running his offer to sell before this Alice's transaction of cancelling that particular order. So, now this attacker has come in between these Alice's two transactions. So, it is front running the second transaction and then attacker will be able to gain out of it. In bulk is that the attacker is trying to run a large set of functions and Alice is trying to buy a limited set of shares offered by a firm on a blockchain. So, what can happen is that this purchase of the attacker will cause the prices to go up and it will force Alice to actually carry out her transactions at a different state, but then it is because of this large set of functions that the attacker is actually trying to carry out. So, we look at this particular example for our understanding that in the context of these markets and exchanges, as we mentioned just now, that there is this on the left there is this unordered mempool, that pool of transactions which is now going to be included in the block, but not yet there in the block. So, it is there in the mempool and it will eventually be added in the context of Ethereum network, as you can see here. So, what we have here is that remember that these attackers could be miners themselves and the miners can decide which all transactions to be put in a block. We discussed about that in detail previously. So, these attackers what they will do is that they will selectively decide which of those particular transactions will go in and in which particular order. So, we see that say there were these set of transactions like and then it was followed by what is of interest to us is this particular transaction about cancelling this order, and then we had something else after this as is shown here. And then what is happening is that the attacker sees that this Alice is going to cancel the order. So, what Alice what the attacker would do is that it will now introduce this particular transaction before that cancellation of the order, and as a result what will happen is this particular order of 100 that will satisfy the initial decision to actually carry out the transaction by Alice, and then this will fulfill it, and then finally this cancel order that is not going to happen. And of course, there are more transactions by order 101 and so on which are going to be there. So, there is no problem with that. Remember that in normal other financial transactions like in share handlings, share markets, exchanges and all, this type of front running is usually considered to be illegal, and if somebody does such front running, then there are legal actions that can be taken. The positive side of blockchain is being decentralized, as we have discussed all its virtues. The flip side is that there is no central authority. So, because there is no central authority, that if some attacker does this front running and you lose out, then you cannot complain to anybody, and also because it is spread across the globe and it is not that one particular such country's laws will be applicable. So, even if front running is done, then there is no way you can come out of it and then try to get some compensations. So, it is easier that is why to carry out such front running attacks in such decentralized such cryptocurrencies like say in Ethereum or in the context of Bitcoin or other types of such cryptocurrencies. Then finally, we will take an example here which is, as I had mentioned, that only one type of this suppression attack that the authors of the paper had noticed, and this is less frequent, but this is also very interesting. So, it was this game FOMO 3D. What it did was that it is very interesting. It said that there is a target time when it will close, and any user who purchased the last ticket will win the money. So, let us call that winning the money to be, say, getting the jackpot. Let us just use the term. So, if say it was a case that on 1st January 2022 at 10 a.m. the entire game will close, and whoever purchased the last such ticket will get the money. But as soon as any such user or a player buys a ticket, the deadline is extended by some time, say 3 minutes as is mentioned. I am sorry, this is not about 3 minutes, it extends by about say 30 seconds. So, if one person purchases a ticket, instead of 10 a.m. or on 1st January 2022, it will be 30 seconds past 10 a.m. on 1st January 2022. If another person purchases a ticket, then it will extend by another 30 seconds. So, it will be 1 minute past 10 a.m. on 1st January 2022 and so on. So, you see that if someone tries to purchase a ticket just before it is supposed to close now, it itself will get extended, and then another person can buy the ticket. So, this way it will keep on continuing, and there was a feeling that it will actually continue forever, because always someone will try to buy it at the last moment and then it will get extended, and then again someone else will try to buy it in the last moment of that extended period, it will get extended again and so on. But then it was found that this actually closed, and one particular person or a group, they actually won it. But you see that the common logic would try to say that it will go on forever. So, how did that happen? Why was it the case that after that person who won purchased the ticket, nobody else purchased and extended it, which in the process would have superseded the claim of this particular person that we are talking about. What this person did is, that is what was actually figured out, is that this person just before when the timer was going to time out. So, it was within 3 minutes of that, what the winner did was, winner bought one ticket, and then what it did, it sent multiple such high gas price transactions to her own DApps. So, this attacker had all these DApps as shown here. Okay. So, these are all attackers DApps, and then the attacker purchased 3 minutes before it was going to close. Now, remember that the attacker did it, and then in order that somebody else purchases the next ticket and extends the deadline, it is important that that transaction also has to go in one of the blocks. What the attacker did was, attacker ensured that no other transaction actually gets committed in a block. That is the trick that the attacker played. How could it do it? It actually flooded with a lot of such DApps and then made multiple calls to those, and which caused the network to be congested, and only the attacker's transactions through these DApps, those were now getting committed to the blocks, and other users who were also willing to purchase the ticket in the last moment and then possibly would have extended this game, they could not actually get their ticket purchase transactions included in the block, and then the timeout occurred, and as the timeout occurred, this attacker was the last person to buy the ticket, and hence this particular attacker won. So, of course, it might be, as mentioned, bribing the miners to prioritize them ahead of any new ticket purchases. So, whether depending on the amount of money that was to be won in this game and so on, the attacker could take some more unfair means beyond flooding with his own DApps transactions, or he could have actually spent more gas, so that the miners will be more than willing to include his transactions in the blocks. If you remember, we talked about some of these underpriced operations in these smart contracts. So, it is possible to do a combination of these types of attacks by ensuring that no other such legitimate ticket purchase transaction will go into the block before that timeout reached. So, you see that this is an example where the whole goal was to delay Alice's transaction, as was mentioned in our context of this very first slide, that this suppression, that the attackers, after the attackers run, the attacker tries to delay Alice's function call, and after the delay Alice's function call is indifferent. So, even if Alice created that ticket purchase transaction after that delay, the attacker does not really care. So, these are some of the interesting types of front running attacks that one can carry out. There are actual instances of these being carried out. So, this actually takes us to the end of this particular lecture of ours today, and to summarize, we have described two types of attacks, namely eclipse attacks and front running attacks. We have identified the importance of these attacks to be detected on a blockchain by the researchers and suggesting remedies, so that this can be fixed in subsequent releases. And of course, we have seen that how different such attacks can be combined, like one can have eclipse attacks and then 51% vulnerability, or we have talked about these front running attacks, and which can actually be made use of in then carrying out other types of attacks, which we already discussed. Once again, please refer to the web resources that we have mentioned, these two particular papers that we have used in this lecture, and also there are other more detailed material as well that came after these papers were published, and they possibly refer to these two papers, which will provide you with a lot of information, and that will help you get much more insight about these attacks that we have so far discussed and more types of attacks. So, because this is the last lecture on blockchain security, so we also conclude about the entire this particular topic of security for blockchains, where we talked about different types of risks and the attacks, and then we went into detailed discussions of some of those attacks. Of course, this is by no means the exhaustive list. There are other types of attacks which get detected from time to time. There are some very interesting such papers even published in 2021 Usenix conference. You can go through those papers and other materials to get a more insight into this very interesting area of security for blockchain. So, that brings us to the end of our lecture today, and also of this particular topic of security in blockchain. Thank you very much for your attention.